So we also have automaticity. And things that are automatic this is when you're processing that information with very little to no effort. It just happens automatically. So I'll give an example of reading, because reading by our age has become automatic. Early on in development, it is not automatic. Children often struggle to read. They have to spell out the words and sound them out when they're reading. So it takes time for them to read every little word. And you can imagine if they can't read the words, to read a sentence and understand its meaning is going to be much more difficult. By automatizing this so they can read each word, they're able to dedicate more cognitive resources or their capacity to thinking about the context or the meaning of a sentence. So as the reading becomes automatized, they're able to dedicate more cognitive resources to other things. For example, thinking about the meaning of a short paragraph. So what does this paragraph mean? What's the takeaway message? It would be hard to do that if your reading ability wasn't automatized, because you'd spend so much of your cognitive capacity focused on actually perceiving the letters and understanding what they mean and making sense of that word. You can imagine that when you read a text with a bunch of words that you don't know what they mean, it's hard for you to take away the gist message because you don't know those words. You've got to look up every single word and maybe translate it to something else. So it's very difficult to do. So by a show of hands, who's heard of the Stroop task? Okay, cool. So this next task, this is just a demonstration of automaticity. So what I want you to do when you look at these letters, and you can do this out loud, so just read the color of the word, not what the word says. So we can start with red, and just go ahead and start right from the beginning. The color of the word. So red, blue, orange, purple, orange, blue, green, red. All right, so now we're going to try it again. And again, you're not reading the word, you're reading the color of the word. All right, so just out loud. Everyone give this next one a try. Green, red, purple, blue, red, green, orange, red, green. All right, so you notice that this was a little bit harder, right? And it's harder because you're automatically reading. Your automaticity, you automatically read the words, and what you have to do is inhibit that automatic response in order to focus on the goal, the task goal, which is to identify the color. And so this is actually a measure of inhibition. We'll talk about that in a few classes, but it demonstrates automaticity here, is that reading is automatic, so it's hard to inhibit that. Working memory, on the other hand, this is like a mental workbench for manipulating that information that's in your short-term memory stores. Working memory is really important for thinking and problem solving. If I were to tell you guys to think of an elephant, just right now, imagine an elephant in your mind. Right now, it's in your short-term memory store. Now if I tell you, imagine that elephant flying. It's got some pink wings and it's flying through the air. Now you're working with that short-term memory. You're manipulating the information that's in there. And you can imagine this might be really important for a lot of educational tasks. So if you're thinking about literacy abilities, you want to be able to read the sentence. You're encoding that sentence, so transferring that to memory. But you also want to be able to take all of those words and pull out the gist information. What does that mean? Right? But it's not just sentence by sentence. If we did that, that would be difficult. You need to keep each sentence in your working memory to comprehend the whole text. It doesn't make sense if you're reading a book and you're in chapter 10 and they start talking about something a character did earlier. It's hard to comprehend that if you can't pull that from your long-term memory, put it in short-term memory, and work with it to see how it applies to the current information. Similarly, with learning another language or performing mathematics, you need to be able to work with information in your mind. So this is really predictive of a lot of educational outcomes. So let's just do a quick demonstration. I'm going to say some digits out loud. Don't write these down, that would be cheating. So I just want you to mentally rehearse these digits in your mind. Okay, you can use whatever strategy you want. At the end, I'm going to ask you to recall some of them. Okay, so you guys ready? So 5, 2, 1, 8, 3, 2. All right, what was the sum of the first digit plus the third digit minus the last digit? Really difficult, right? So it would be 5 plus 1 is 6, minus the last digit, which is 2, would be equal to 4. Right? And so you can imagine that's really hard to do. That's one of the tasks that we would actually use to measure working memory. I could also ask you to recall the digits in reverse order. So you have to take what you know and recall them in reverse order. These can be really difficult tasks. So you can imagine that young children really struggle with this. You know, they have to be able to encode this. I saw a few of you using a really good strategy. So we're thinking about the mechanisms of change. So you're using a strategy. One of that is rehearsal. Right? So you're rehearsing these numbers so you can remember them. Then when I ask you to solve a math problem, you're like, oh no, now I gotta think about that. And so you're using strategies to be able to recall that and that type of thing.
The purpose of this activity, I did this as an undergraduate and found it really interesting to do. I want you to get a sense of what it's like to test a hypothesis and, revise that hypothesis in light of new evidence. So this should get your critical thinking skills going. And your goal is to understand the underlying rule of a sequence of numbers. So on the worksheet, there's a different sequence of numbers than the ones on the PowerPoint right now. And we need to figure out how the world is as a scientist, but you don't really know. You have to develop a hypothesis and test it. So what I'm going to do is I'm going to break you guys out into just random breakout groups. And I want you to think of a hypothesis. What do you think the underlying rule is that guides this number sequence? And the rule could be anything at all. So for example, I might hypothesize that the rule underlying 357 is that it increases by 2. And so to test my hypothesis, you can propose any new sequence of numbers. It could be, 11, 13, 15. And then when you have a new sequence, I just want you to raise your hands in the group. I'll pop into the group. And all I'm going to do is I'm going to say, yes, it does fit the sequence, or no, it doesn't. I heard some interesting tests of your hypotheses. So a lot of people proposed very similar number sequences. Does anyone have a hypothesis about what the rule is? Yeah, Hunter.
Just add 2. That's what my guess is.
Add 2.
Add 2 to even numbers.
So yeah, that's one that I heard is increases by 2 or all even numbers or 2n. That's a good rule too. And many of the groups that I was able to jump into, the way that you guys tested that was by proposing, for example, 8, 10, 12, right? So if you did propose 8, 10, and 12, I told you that yes, that does follow the number sequence. And that's typically what happens when I've done this demonstration before. And what's interesting is that what you've done here is develop a confirmation hypothesis, right? So you think that the rule is 2n or increases by 2, and you test a sequence that confirms that hypothesis. But let's say Anastasia bringing in some math terms. I like that. So it looks like the rule is multiples of 2. 2 by 2 is 4. It's increasing by 2. Let me tell you guys another number sequence that a different science team proposed, but that also follows the rule. Can you guys see that? So here's new data that's come in, 1, 1.5, and 6. And this also follows the rule. So in light of this new data, we would all have to really refine our hypothesis, right? In order to figure out what the actual rule is. And one of the things that's interesting that most people end up doing when I do this demonstration is you search for confirming evidence, right? And this is just indicating the confirmation bias. One of the things that we want to do in science is we actually want to provide evidence against something in order to show evidence in favor of it. And that's kind of like a backwards way of thinking, right? It's pretty confusing to think about that. So if I had a hypothesis that the numbers increase by 2, that would fit the rule. If I wanted to show that that is the case, rather than providing cases where it does fit the rule, the best way to test that hypothesis is by testing whether something doesn't fit the hypothesis. So if I propose the numbers 1, 1.5, and 6, and that does fit the rule, well, I know that my rule is wrong, right? So you've now disconfirmed your initial hypothesis, which you can reevaluate. So this is the idea that you really want null and alternative hypotheses that you can test in order to provide evidence against your hypothesis. Until ultimately, I'm going to provide another number sequence. This one also follows the rule. But this one does not. So 543 does not follow the rule. So anyone have a new hypothesis? Yeah, Olivia.
So this might be a stretch, but just that the next number has to be larger than the last number.
Good. Yeah, so that's a great hypothesis. The next number has to be bigger than the prior number. How can we test that other than this 543 sequence? Can anyone think of an alternative hypothesis that we can use to falsify the idea that the next number needs to be bigger than the prior number? So here's our current working hypothesis. Oh, messed that up. Good, so one hypothesis or one data is 555. And that does not fit the rule. So now we've ruled out this alternative hypothesis that maybe it can just be any 3 numbers without decreasing. And it doesn't fit the rule, so maybe our initial rule that any increasing 3 numbers is the right rule. And ultimately, the point of this exercise is to point out this is kind of like what the scientific method does. We never prove anything, and some of the strongest ways to provide evidence in favor of something is actually to provide evidence against all of the other alternatives. So what we're typically trying to do in the scientific method is to provide evidence that I have this idea, let me do everything I can to show that it's not accurate. I'm going to try and find evidence that falsifies it. And if you can't falsify it, if you can't find evidence against it or not supporting of that idea, well then it must be that sequence that you proposed. We could do fractions, maybe it's all whole numbers or integers. And ultimately we would get to the final rule, which is correct, that it is any increasing 3 numbers. So does that make sense?